Welcome to resistor inductor circuits or RL circuits. So RL circuits consist of a resistor and an inductor connected in series or parallel to the power source. So here are a few key concepts we need to familiarize ourselves with to get started. So we have Ohm's law, which is the first one, and then we have the inductor, which is represented using this L, and then this right here is the circuit symbol. So this is the symbol of an inductor. So the inductor stores energy in a magnetic field when current passes through it. So also note that it opposes the changes in current. We also have something called the inductor voltage, or basically the current across the inductor. So this is given as VL is equal to the inductance. This is the inductance, which is measured in henries. So that is henries. And then multiply that by the derivative of current with respect to time, which is basically the rate of change in current. So let's talk about the RL circuit behavior. So initially we have the inductor, let's say so let's talk about the circuit behavior of RL circuit. So initially we have the inductor, which resists the change in current due to the buildup of its magnetic field. So when you look on the right, we have an RL circuit. So we have the inductor right there. So let me remove those. So we have an inductor and a resistor in parallel right there, and then we have a power source. So initially, let's say the switch is open. So initially there is no current through the inductor and there is no current through the resistor. And now let's close that switch. So at T0 we have now current through the inductor and the resistor, but then now there's a change in current from 0 to something else through the inductor. So now the inductor acts more like a resistor. So there is current going through the inductor and there is current going through the resistor. Now over time, as t tends to infinity, or t is almost equal to infinity, the current through the inductor increases and reaches a steady state, which means the inductor now behaves as a short circuit. There is zero voltage drops across the inductor. So now that the inductor now behaves as a short circuit, there is no current going through the resistor. So all of the current goes through the inductor. And this happens when T is almost like the switch has been closed for a long time. So we can say T is almost equal to infinity. So now let's talk about the time constant. So the time constant is the measure of how quickly the current reaches its final value after the change in voltage. And it is being calculated using this equation. The time constant is equal to the inductance divided by the resistance. Now let's talk about the natural response of an RL circuit. So this refers to the behavior of an RL circuit when there is no external power source applied to the circuit. So the circuit relies on the energy that is stored in the inductor to sustain the current flow. So let me show you an example using this diagram right here. So we have an independent current source and then we have an inductor over there. So let's say we have the switch is closed. It's initially closed, right? So let's say the switch has been closed for a long time. So when the switch has been closed for a long time, this inductor now becomes a short circuit. And when it becomes a short circuit, there is no current going through all of these other resistors. So basically before the switch is being opened, we have this part of the circuit. So we don't consider that part of the circuit. So let's say now we open the switch So let's say now the switch is open, just like that. So when we open the switch, we disconnect this part of the circuit from this independent current source over there. So we only have this part of the circuit. So this part of the circuit functions without the independent current source, but relies on the energy that is stored within the inductor to sustain current flow. So I will show you a little bit of a circuit simulation to show you what I'm talking about. So we're going to do a circuit simulation for this circuit. So I'm just going to go here and then I'm going to show you the simulation. So I'm going to close the switch and then I'm going to run this. So initially we have this type of circuit, and then let's open the switch. So when I open the switch, now I disconnect this part of the circuit from that part of the circuit. So this part of the circuit does not have an external power supply or the independent current source. So basically the circuit gets its energy from the energy that is being stored within the inductor. So this is what is known as the natural response. So that part of the circuit we don't really consider it in our calculations. We just look at this part of the circuit after t is equal to 0. So initially, before t is equal to 0, this was our circuit. So let me reduce the speed, the simulation speed. So this was our circuit. And then at t is equal to 0, we open the switch. When we open the switch, and then there's an energy that has been stored within the inductor, and then this part of the circuit will use that energy that has been stored within the inductor. And then on that part of the circuit, we usually just ignore it in our calculations. So remember we said that before t is equal to 0, when the switch was closed, there will be no current going through these resistors, the 10 ohm resistors, because of the inductor, which will be a short circuit, and all of the current will be passing through the inductor and not going through the 10 ohm resistors. So let me speed up the simulation to show you this. Okay, we're gonna have to wait for it. You see, the current going through the resistors is decreasing over time, and the current going through the inductor is increasing over time after t is equal to 0. So as t tends to infinity, the current going through the inductor increases, just like what I've stated in this example here, right here. Over time, when t is almost equal to infinity, the current through the inductor increases and reaches a steady state. So the inductor behaves as a short circuit. So there will be current going through, all of the current going through the inductor and no current going through the resistors. So I'm just going to show you. You see, there is no current going through those. Well, there is a small current, but over time there will be no current going through those resistors, as you can see. So this is what I've been talking about.